Work 3 is out, due the 18th. I don't even know what day that is. It's coming up. Some people have already committed, so that's awesome. The intent was for people to finish pretty early, or to try to, so that they could get done with the final project, or get started on the final projects. Readings are posted for Wednesday. Let's talk first about final projects. So anyone who sent me things up to about, I think 15 minutes ago, I commented in email or in line, clarified, asked for more things in some cases, asked for clarifications in others. I'll send TF assignments later today. Some people still have not been approved, though, on their final project. Basically, I said, you need to do this, you need to do that, you need to come back with something else, something more. You need to address that soon. Time is wasting. The Harvard CS Fall poster session is on the 12th. I posted on Piazza asking if anyone was actually going to do a poster instead of the screencast. No one has replied, so maybe that's not going to happen. But do post let me know soon if you're planning on doing that, so I can let them know to make sure and reserve space for you. The readings, so we'll talk about them on Wednesday. Read one or the other, or both if you're really curious. I kind of like the particle simulation in CUDA one more than the matrix multiplication. The matrix multiplication is very interesting if you're planning to do some deep CUDA optimization. It talks about, what basically delves pretty deeply into the hardware and what the sort of performance of different parts of the memory and computational behavior of the GPU is. So it's pretty cool on that level, and it goes through a bunch of steps that are interesting. The particle simulation is a nice little, how do we take a it's obvious how to do something like median filter, how this maps well onto GPU where you have a bunch of independent compute. Because it's really a structured, fairly straightforward computation, and you can map it to each pixel independently. It's not obvious how you do particle simulation where things are moving around and not always in the same place, and still map it efficiently into this this crazy super scalar or super parallel architecture efficiently. Right? You could easily do a bunch of computations, and all of them would be reading global memory like we saw in homework 2, particles looking for other particles, things like that. But they can do surprisingly well. There are a few high-performance physics libraries that are used in games and other things like that for simulation based on that work. And then the efficient transpose in CUDA is very short. Talks about it's basically almost the example we went through last lecture of here's a transpose operation, how do we make it faster? It's a little bit different. It's not going to map a single thread to each value that needs to be transposed. It's going to do more work per thread than just a single value to make it more efficient. But it's important to understand that, we've talked about a fairly limited way of mapping computation onto problems, where we basically launch a thread for each small subproblem. That's not always the best way, particularly if you've got very little compute, which transpose has no compute. It just has memory reads and writes. And so in that case, you have to do basically more computation per memory read to be efficient. And so that's what that does. Anyway, they're all good. Post some discussion on Piazza or bring questions to class. All right, today, I want to talk about OpenCL versus CUDA because CUDA is dominant in the market. OpenCL is nice in that it runs on a bunch of different hardware, including CPUs. CUDA is NVIDIA only. But I want to talk about the links between them and when you're looking at CUDA code, how to read that, how to translate between the two in your head. And then also a little bit about GPU future developments, where things are going in CPU and GPU space. So the differences between OpenCL and CUDA are not that large. They're both based on C. The keywords are different, obviously. So you get some things like global is called device in CUDA. Local memory is called shared. Instead of barrier, you have sync threads, and you have a bunch of different variations. There are some things that don't map between the the 3 types of barriers you have in OpenCL based on local, global, et cetera. There are different sync threads. There's also thread block and a few other functions. Those you just look at the docs. When you're doing the boilerplate at the beginning of each function, Um, Instead of using the functions to get the dimension and the size and position and all of that based on different, how the kernel has been launched, in CUDA it's all extensions of these built-in variables. So you'll see these just accessed within kernels written in CUDA without any declaration. They're built-ins. They have an X, Y, and they actually have an X, Y, and Z. CUDA always supports three-dimensional and no more. OpenCL supports three-dimensional and possibly more. But you can just map between them this way. You get gridded in, they're blocks instead of work groups. Then your local ID is your thread index. And then you have some other, then in just terms of terminology, instead of a thread or a work item like you have in OpenCL, you have threads. I mean, I've been calling them threads because we have talked a lot about threads in other cases. In OpenCL, they're technically always just called work items and work groups. But threads, thread blocks, and then local memory and shared memory are different things. The other thing to be aware of is CUDA is a very strong bias towards 32. All the processors work with 32 threads in a warp. You'll see things called warps and half warps. All the work that actually happens on NVIDIA is in these blocks of 32. And so thread blocks will often just be 32 by something or just operate in 32. And you have a bunch of operations that exist only in CUDA for dealing with those blocks of thread. Let's talk about tools. What can what do you have available? On NVIDIA, CUDA is really well supported. All right, it's much nicer, actually, I think, in general, to develop in CUDA if you have access to a graphics card, and particularly if it's right in front of you. Compiler debugger, you've got a nice profiler, there's a memory checker, there are various other tools built into the development that they distribute or can be integrated with whatever development environment you're using. And on OpenCL, it's really up to who are you targeting, right? Are you running on an AMD processor? If you're using the Intel tools, then you have Visual Studio plugin for debugging and profiling, but then you're stuck under Windows for Visual Studio. NVIDIA has limited support for OpenCL in general, just because they devote all their time to CUDA. The hardware is reasonably well supported, but as you can see in the, if you look at the OpenCL matrix multiply paper, it compares CUDA's vendor implementation of matrix multiply to OpenCL's version of matrix multiply, which is just written by someone in open source. And then their best tuned version, they never get close. They're always about 50% off or more in terms of performance compared to what NVIDIA can produce. Because NVIDIA has sat with their engineers and really optimized the matrix multiply code much more than they're worried about OpenCL performance. In terms of third-party library, oh, sorry. No, you will not get the same performance. So NVIDIA produces both compilers. Actually, maybe that's not true for if you use Apple's OpenCL, but I think they use some of the NVIDIA tools. And it produces similar code, it has to at the bottom, but it's just not as heavily optimized. It's not as, they haven't done as careful a job partially to expose what's available on the hardware in OpenCL, partially just making their compiler and what you write tuned to it. A lot of the parts of the CUDA matrix multiply and other libraries like that are done by NVIDIA are potentially going to have some hand-coded, assembly in there to really make it fast. And thinking about, how long exactly is this multiply going to take, and where can I place the next operation in this chain? So CUDA is also, it's just more popular in general. They produce, so OpenCL has various sparse and basic linear algebra and FFT and whatever else. And there are other implementations that are available. They're kind of scattered. They're implemented by different people. These four are sort of well supported and done by people who are at companies that have OpenCL versions and so are motivated to have those. But CUDA has all the same, plus a bunch of other ones. And these are all supported also by NVIDIA and well integrated. or by companies whose livelihoods depend on NVIDIA's hardware. So there are a lot more, you know, the deep neural network stuff, the CUDA math extensions. There's just the environment is more rich. NVIDIA has been there longer, basically. OpenCL lagged behind for a long time. They arrived around the same time, but didn't take off as fast. And so they're still playing catch up, basically. And the one place where OpenCL does do better is portability. Right? You can write OpenCL code, and if you don't stress the hardware too much and are not trying to optimize too much for, you know, particular launch sizes or work group sizes or memory behavior, OpenCL can be, you know, it can run on most CPUs, a fair number of GPUs. Still might not be trivial, porting from one to the other, dealing with hardware variations. You might have a very limited work group size. Performance is not going to be arbitrarily good. You know, it's not going to be anywhere near peak for arbitrary code. So you'll have to do tuning. And of course, CUDA is NVIDIA only. The hardware support between the two languages. OpenCL is the open standard. Hooray, that's good. Unless you've dealt with a bunch of open standards before, like I have. They almost always, the first couple iterations are almost always good, and then they start falling into this, oh, I don't have it up here, actually. Maybe it's on the next one. They almost always start falling into these vendor extensions. You know, there's a standard process, they want to upgrade, but it gets bogged down, so someone's like, oh, we'll just do these extensions. We'll expose this nice hardware feature to everyone. They just have to call this function to enable it, then they can use it in their code. The problem is people start using that, and then your code isn't portable anymore. Your algorithms come to rely on this vendor extension very quickly, and OpenCL is starting to do this. There's several vendor extensions already in 2.0. Unless they come together to basically force these into the standard or find some way to make them well supported, it'll probably diverge into, you know, you'll have OpenCL for Apple, you'll have OpenCL for Intel, and you won't be able to actually translate code between them. So it erases somewhat of the open standard benefits. AMD uses, one good thing is AMD's, all of their general GPU computation is through OpenCL. So they're motivated the same way NVIDIA is to make CUDA good and popular. AMD is doing the same thing. AMD is a lot smaller than NVIDIA though, so. And on CPUs, OpenCL is just less interesting than OpenMP, right? For CPU vendors, OpenCL is nice to have, but it's not necessary. Their core business, you can get it from OpenMP, you can use AVX, you can do multi-threaded programming or whatever. You don't need OpenCL to get high performance on a multi-core CPU. OpenCL, yeah. It's advantageous to use it. But if I'm Intel or some other chip vendor, most of my work is going to be producing the Intel compiler, right? And making it still, I mean, my job is to make single threads or multiple instances of single threads run quickly. It's not I'm not generally targeting things where I have thousands or threads or a thread per pixel. I can still support it, and I can probably use, you know, my knowledge of the hardware to produce a good compiler for cases like this. But it's not going to be my primary mission, right? If I'm producing a compiler for my chip, I'm going to target most of the uses, which are going to be things like, you know, how GCC or Clang works. Or Intel compiler. That's going to be where I'm going to spend my sort of software compiler knowledge more than supporting OpenCL, which is fairly limited in who can use it. It's limited in the tasks that it applies well to. So it's not how I give you access to the power that I've put into the chip, right? I do that through a regular compiler. So I talked about this. OpenCL and CUDA are about the same in terms of functionality, especially with OpenCL 2.0. But some of it's only available through hardware vendor extensions. And these are, like I said, almost always painful in my experience. They lead to fragmentation, they lead to poor portability. In CUDA, there are functions. The one thing about CUDA is depending on the version of, you have a bunch of different versions of CUDA from 4 point something to 7.5. And you have a bunch of different versions of hardware. And so there's a big matrix of what can I program to and what can the hardware actually do. And so writing portable code for CUDA, even on different NVIDIA hardware, is often a pain. So you often end up writing for just like one generation of chips or cards if you're implementing something for CUDA, and you have a fairly limited, even across NVIDIA hardware, fairly limited portability.
Are they backwards compatible though? Like CUDA 7 that comes with the 5 or something?
In general, yes. So in general, the CUDA 7, you can take CUDA 5 code and it'll just run. You can use the CUDA 7 compiler and it'll just work. And in general, also, as you get to the later hardware, it has more. It always has more. Almost always has more features. So what to use? I don't know. It's a tricky choice. I tend to use CUDA because it's more popular in code and research. If you look at publications, about 6 times more common to see CUDA than OpenCL. In deep learning, which I use, and machine learning, CUDA is much more common. There are more jobs in CUDA by about a factor of 2 based on various searches, 1.5 to 2. OpenCL is more portable, which is nice if you're going to be targeting multiple things. Generally what I say is just do what your friends do, or your company does, or whatever, right? If you've got your friends can be someone who have provided code. If you're trying to solve a particular problem, and someone has provided code that solves something nearby, or can be adjusted, then use whatever that uses. It'll be easier. Once you know CUDA or OpenCL, moving between them is not going to be that hard. The concepts are going to be about the same. If you are doing some heavy optimization, you're going to have to learn about the hardware and how it interacts with OpenCL or CUDA anyway, and so it won't matter so much. So just use what provides the best environment to you in terms of other people to talk to, other code to use. All right. Any questions about OpenCL CUDA relations or differences or commonalities? All right. Let's talk about the future. So this is a typical desktop situation, right? With a graphics card and just some of the bandwidth numbers, right? You can talk to RAM depending on how new it is. I think that's a DDR3 something. 50 to 75 gigabytes a second, getting data from RAM to the CPU. As we've talked about, GPUs are bandwidth machines, right? They have 4 to 5 times more bandwidth to their memory. This is much smaller in general, maybe a factor of 10 than that. And then there's this horrible, horrible thing in the middle, the system bus, right? The PCI bus where you actually plug in the card, which is 16 gigabytes a second on a good day. And if you're doing high performance stuff like on a cluster, then you've got 16 gigabytes per second shared, right? We haven't talked about this. I didn't talk too much about how much data transfers limit your computation on GPUs. Things like the median filter and things like that. Unless you're launching multiple iterations on the GPU at once, it's very inefficient, actually, to take all that data, push it across this tiny little like straw of the PCIe bus, and then read it back. If you time the median filter code with actually just a single iteration, including the transfer times, it'll be much slower than just doing it by hand because of this problem. So NVIDIA and other people, IBM with the Power PC and a few other vendors said, this is horrible, especially for high performance computing. Let's fix this. And they came up with a thing called NVLink. Almost anything that's going to start with CU or NV in the NVIDIA world, which is 80 gigabytes a second, right? So between 2 GPUs, they have a special cable. They don't go across the bus anymore. Now you have 80 gigabytes a second, which is faster than RAM, right, at the high end. You still got the PCIe bus, which is kind of a pain. And then you've got very fast memory here. But So you've got these new interconnects. You've still got the PCIe bus, which is kind of terrible. And it's actually that this is broken up into 4 20 gigabyte a second channels. And the way they work is you can use them to hook to the CPU if it's PowerPC or one of the other vendors that are doing this. So now you've suddenly got 40 gigabytes a second between the CPU, video card. It's nice. You can start doing crazy things with interconnect if you've got like a super computer, right, where you've got 4 GPUs per CPU. All kinds of transfer. This can speed up some computations by a factor of 3 or so for Fourier transforms or simulation across multiple domains. So here's, sorry, go ahead. Oh, so how did that happen? All right, so this one is what we have on a sort of default machine, right? I buy a computer and I buy 2 GPUs, even if they're the hot new, next year GPUs that I get somehow magically. They have a special cable, I connect them, and now the GPUs can talk that fast. But the next generation of CPU from some versions of PowerPC, and maybe some AMD processors as well. Intel's not so interested in this because they're starting to see NVIDIA as a competitor, and these other people as competitors. We'll have a port where you're like, instead of talking across the PCIe bus, I have a direct connection between somewhere near the CPU and my GPU card. It's not just the usual like, I push the GPU card. It's like another cable. Or possibly a different, it's hardwired in. So now now I've got these, basically every card and every CPU has 4 ports. Each of them does 20 gigabytes a second, very low latency too. And now you can just start plugging them in. So that GPU, if it has 4, and then it can chain to the next one. Or I could have, another 2 going across. All right. It's unclear what it looks like. It's the future, right? It's probably some glowy, I imagine it glows and is silvery. But so you can do it with, you can build up these meshes. And as I said, it can be on the CPU. So what's interesting here? All right, what looks bad in this? PCIe sucked, so now we threw it out. Now what's horrible? Link to RAM, right? This RAM, it's large, which is nice, and cheap, which is nice, but it's slow and cheap, which is not nice. And if it's 50 to 75, each of those is 40 gigabytes a second, right? Right, if I've got 240 gigabytes a second here, and just one GPU card, which I can talk to at 80 gigabytes a second, very low latency. Not as low latency as RAM, but still. And this is now the slowest thing. If I'm computing with something that's not very large, maybe I'm doing video processing. It doesn't take a huge amount of memory, but it's very bandwidth intensive. All of my computation, where am I going to store that video? Am I even going to touch this RAM? I would never go across that, right? I'm just going to do all of my compute through the big connector. I'm just going to treat it all as a big block of RAM, right? This already exists in OpenCL as well. On NVIDIA, it's called unified memory. You just say, I want some memory. I want it to be fast. I want it to be regular. I need a lot. If you ask for a lot, it'll put it over here, and whenever you access it, it'll be slow. If you ask for not too much and you ask for it fast, it'll put it over on the GPU, but you'll never know. And you'll be able to access it the same in all your code, whether it's running on the CPU or GPU, and it'll just find out where it is on the fly. So this makes things a lot easier. Some of the code gets a lot cleaner in particular. And then just using the CPU, you just have, or using the CPU or the GPU, you just have things that, I want this to happen in parallel. I want this to happen in serial. And it just goes so. So now we've got RAM down on the GPU, which is acting as another sort of RAM, or just extra RAM for our general compute. The other thing is they're starting to make this so that you have more. They're actually making it more dense by making 3D RAM, where they stack it some number of layers deep, and then move it closer to the GPU. So not as close as local memory on chip, but from multiple inches down to half a centimeter or so to reduce the latency. So you've got this big slow RAM. You've got local, which is small and super fast. You've got smaller than CPU RAM on the GPU, so not as much here. It starts to look like this crazy, it's like NUMA, right? Where some RAM is close and some RAM is far away. And now you've got some RAM that is close and fast and far away, or, plus the compute is also distributed. So you've got this right, the non-uniform memory addressing and compute, where some things can be done very quickly. Some simple things can be done in parallel on the GPUs using local memory. A lot of the compute can just go through the RAM here to be faster. If you've got a really large amount of data, or a large amount of data, you have to store it here. But maybe you can cut pieces out, things like this.
Why doesn't the access to the big RAM get faster when the other RAM gets faster? Like, can't they speed that up somehow too?
So why not put another NVLink here, basically?
Yeah, like,
or something like this.
if the pipe over there is a terabyte per second, why can't you get like something like a half a terabyte per second?
So it costs a lot.
Oh, does it? Okay.
That's the thing. So to get this, they have very wide buses. Those are expensive and difficult to send very far away. So all the RAM here is stacked. They make it more and more dense, and they push it in very close to the GPU. They actually just kind of, they're a bunch of little RAM modules around the GPU. Whereas this, I mean, thinking way back to our graphs about RAM density and things like that, right? RAM density is following Moore's law and doing better even as we find better and better ways to store information densely. But the throughput doesn't get better, right? Because the buses, we can't really make them wider. It's hard, it's easy to make denser RAM. It's harder to make denser RAM that you can access faster. And so you could probably boost this. You could probably get it up to the NVLink speed, hopefully. I mean, the next iteration, DDR4 or whatever, probably would be that fast, or close to. But the expense is, it's difficult to offset that expense. Whereas here, you're getting a whole bunch of compute, too. Right? And this is really, this terabyte a second is really to enable that compute to be possible. It's not. That's why it's smaller, too. I mean, this will be larger, but it's not going to get anywhere close to this. This is going to grow faster than this can by just economics.
So you could put a small amount of very fast RAM.
Yeah, you could do that. You could pull the same trick here, right, and put it on the CPU. Then it's like a cache, but you have to manage it. It's kind of complex. I mean, if you were going to do that, you would probably just turn it into another cache, another like L4 cache. It was very large. But the way the CPU works, it's not going to do that much good, right? Especially with CPU hit rates, cache hit rates are very high, right? You hit L1 above 90% of the time. And then to get rid of, and then you have L2, which is 10 times as large as L1. That gets rid of another 5%. To have it again, you have to have another 10 times. And to have that again, you have to have you get an exponential fall off in how useful cache is, just because it's so effective at the top levels. So it's possible. And the main thing is, I don't necessarily want to program this machine, right? It's going to go fast if I can figure out how to use it. But I basically have two things that can do compute. I have four places that I have to think about where memory is. I've got my cache on my CPU, which I don't have control over, and then three that I have to manage semi-explicitly. I have to think about where the data is. I have to think about what sort of compute I need to do. I mean, it looks exciting, but exciting is not necessarily good. Now, but it's already also just happening. I mean, this is not just on the CPU. I mean, this is not the supercomputer only world. I mean, the NVLink is really targeted towards, and will be going into a couple of large compute centers. This is the Tegra K1 mobile processor. It's no slouch, right? It can easily be a quite handy laptop. It's probably about, so just this part is a quad, well, it's a 4+1, which I don't know what that means. I mean, one of them is small, so it's a +1. I don't know what you can't do on that processor, that core. 4 ARM cores, running at 2.3 gigahertz. It's not, I mean, this is what my laptop does. And then it's full of GPUs, right on chip. All the memory is just the same memory. It's all just memory. It's called a mobile processor, but their plan is to push these up higher and higher until your standard desktop, laptop, whatever, has the GPU built in with some sort of weird unified memory, some of it fast, some of it slow. Again, the same picture that we just were showing, but everything just jammed onto one chip. So we're going to see a lot more of this. It's going to be both a combination of, multi-threading programming to get efficient use out of things that can't be run on the GPU, and then a whole bunch of compute on the GPU. And partly right now, this is just being used to make games look good, because there's money in games. But also just in general for compute, doing sound, doing any sort of stream processing. So programming on these things is going to be kind of cool, kind of weird. You're going to have to think not just about cache and multi-threading, but cache and multi-threading and GPU access to local memory and things like this. So basically, just imagine that we took homework 2 and homework 3 and just blended them together, made you do them all at the same time. Next time. So it's kind of interesting. I don't know where it's going to go. They're pushing these towards, NVIDIA's plan is to push this into, start putting these out as phones and laptops and desktops and whatever.
So doesn't NVIDIA markets this chip?
This is what's inside that little board that I brought in. This is the Jetson TK1 board.
Oh, okay.
Chip.
Okay.
Floor plan. So there are 192 little processors and then the 4+1. I mean, they're aiming this at phones too, like trying to push it down even farther. It's kind of interesting to think about your phone having a GPU that 5 years ago would be top of the line. And it runs, this is like 5 watts of power too, which is really amazing. Right, at the peak, 5 to 10. So anyway, that's as far as I know into the future. That's only like a year out. After that, it gets just crazy. So. All right, I'm going to end a little early because I have a bunch of people I have to talk to about final projects. If you haven't got approval, you should probably come down and talk to me now. Wednesday, the readings. Friday, OpenCL wrap-up and review. We'll just talk about a couple more things about efficiency in terms of overlapping compute and transfer and out-of-order queues in OpenCL. If there are questions that you want answered about OpenCL or CUDA, particularly for the homework, post them on Piazza. We'll talk about them then. Any other topics in there that people are curious about. If you still have to talk to me about final projects, catch me right now, and let's hash things out.